Welcome. We'll be discussing catchment characteristics today. A catchment is essentially the area of land that contributes runoff water, and it's also the potential location for a best management practice, or BMP. This presentation, authored by Marty Wanyalista, will introduce you to these concepts, often in the context of tools like BMPFast. Our session today focuses on understanding how catchments are defined and what data is necessary to calculate annual runoff and pollutant loadings. We'll begin by clarifying what exactly a catchment is. Then we'll delve into the practical aspects of working with the BMPFast software, specifically looking at the inputs and outputs required for its worksheets. A key part of our discussion will involve user-defined event mean concentrations, or EMCs, and how to handle catchments with combined land uses. This includes learning how to calculate a composite curve number and event mean concentration when you have multiple land types within a single catchment. Finally, we'll explore how to account for wet pond areas and other modifications that can influence your loading calculations, particularly the opportunity to treat wet ponds as if they are not contributing annual runoff water from rainfall. Let's define two important terms. First, a catchment refers to an area that collects and then discharges runoff water, either to a surface water body or into groundwater if retention is involved. Importantly, it's within these catchments, or at their discharge points, that we find the potential for managing this runoff through what's known as a best management practice, or BMP. A best management practice for stormwater treatment is a practice or often a combination of practices that has been rigorously evaluated. This evaluation involves research, field testing, and expert review to determine its effectiveness and practicality, considering both economic and technological factors. The primary goal of a BMP is to improve water quality by significantly reducing excess nutrients and other pollutant loads in the water. While many traditional BMPs are well established and described in resources like Appendix O and Volume 1 of the applicant's handbook, there are also provisions for proposing alternative BMPs as specified in Section 9.5.2 of the same volume. It's always a good idea to review the full definitions in the applicant's handbook for a complete understanding of these assessment procedures. A catchment area is fundamentally defined by a specific point of discharge, which often aligns with a potential location for a best management practice, or BMP. The configuration which dictates the flow direction within this area is crucial because it allows us to precisely track the movement of runoff water. This tracking is vital for understanding where and how to best apply the removal mechanisms of a potential BMP. The program is designed to be highly flexible, allowing for an unlimited number of catchments and configurations to be modeled. For instance, BMPFast has been utilized to provide assessments of annual loading for as many as 17 catchments over a significant 426-acre watershed. This data is courtesy of Ferguson. Now, let's open the BMPFast software. Before we proceed with any analysis, it's crucial that you always enter the site characteristics data first. Once that's complete, you can select Yes for the groundwater analysis option. Please follow along with the data shown in the upcoming examples as you use the software. This hands-on approach will significantly help you develop proficiency. This particular slide introduces the Watershed Characteristics worksheet, which is where you'll enter the data for one or more of your catchments. It's essential to begin by entering a catchment name and its associated land use type. You'll also input runoff-related pollutant data, and these data should be documented for both pre-development and post-development conditions. Notice the Help buttons indicated by a question mark, which provide assistance as you work. There are also calculation buttons available that you can use to determine specific input data, such as a composite curve number or an event mean concentration, which you might want to document. The great thing about this worksheet is that there's an unlimited number of catchments you can define. We highly recommend that you enter the example data shown in your software to become more proficient in using it. When dealing with a catchment that has multiple land uses, each with its own curve number, we need to determine a composite curve number for the entire area. This composite curve number, or CN, is essential for accurately calculating the overall runoff volume from the catchment. The correct approach involves first calculating the runoff volume for each individual land use segment using its specific curve number. Once you have the runoff volumes for all the different segments, you then sum them up to get the total runoff for the entire catchment. Finally, you back-calculate a single composite curve number that would yield this exact total runoff volume. It's crucial to understand that simply taking an average of the curve numbers, as shown by average CN equals 72.5, or performing an area-weighted average, like area AVG CN equals 52.78, is incorrect and will lead to inaccurate runoff predictions. These simple averaging methods must not be used. The proper back-calculation method, as illustrated here, results in a composite curve number of 64 for this specific example. We're now going to discuss the contribution of wet ponds to loadings, specifically focusing on the annual runoff coefficient, or ROC. For each catchment, we calculate this annual runoff coefficient. Conceptually, ROC represents the ratio of the annual runoff depth, R, to the annual precipitation depth, P. By utilizing this coefficient, along with the precipitation and the specific area, we can determine the total runoff volume for a given site. This runoff volume is a critical value, because when you multiply it by the event mean concentration, you arrive at the total loadings. Now, there's an important consideration for wet ponds, particularly in Florida. Due to the fact that annual evapotranspiration from these ponds is often approximately equal to the rainfall they receive, it's frequently assumed that there's no net loading contributed from these wet pond areas. However, it's crucial to understand that whether or not you can apply this non-loading option will be determined by the relevant review agencies. Furthermore, beyond typical runoff, you may also need to adjust your loadings calculations to account for other sources, such as pumped flows or contributions from groundwater. Here, we're looking at the user-defined event mean concentration, or EMC, values for a specific scenario. For the disconnected impervious area, the agreed-upon EMC was set at 1.80 milligrams per liter. Comparatively, the pervious area had an EMC of 1.20 milligrams per liter. It's important to note for this particular example that some of the directly connected impervious area, or DCIA, is indeed disconnected. We've covered several key concepts in this module. First, we defined what a catchment is, understanding it as the area that contributes runoff water and also serves as a potential location for implementing best management practices, or BMPs. We then explored the worksheet inputs and outputs, looking at the specific data used to define runoff volumes and pollutant loadings. We also saw how to enter these values into the BMPFast software and observed how EMC values can change based on various factors. A crucial feature we discussed was the ability to use user-defined EMCs. This is particularly important for scenarios involving mixed land uses or when you need to input data not prefixed within the software itself. Furthermore, we examined how to calculate composite curve number, or CN values, especially when dealing with combined land uses, which directly impacts our EMC calculations. Finally, we looked at how the presence of a wet pond area influences our loading calculations. This included understanding modifications due to pumped discharges, or the assumption that wet pond areas might not contribute an annual load under certain conditions. You have now completed our discussion on catchment characteristics and how they influence annual runoff volume and loading. We encourage you to explore other modules to gain a more comprehensive understanding of the full assessment process and the application of the BMPFast software. Additionally, consider pursuing your certificate of competency to validate your expertise. Thank you for viewing and listening to this presentation.